session. We will first look at introduction to strain gauge, its working principle, gauge factor, and then we will try to look for some materials which are used for strain gauge. Now before we go into details, let us try to answer some questions here. Is it necessary to measure amount of stress an aeroplane wing can handle until it fails? Have you ever given this a thought? Wait a minute and try to answer. See, aeroplane wings need to be strong in order to fly correctly. Testing the amount of strain a material can take allows engineers to find the strongest material for their plane. So yes, this is necessary. Next, have you ever imagined how bridge maintenance companies work? How can we get to know if a bridge becomes weak at some points so that we can fix it before the bridge breaks? Now cities are full of bridges nowadays, isn't it? So we as engineers, we need to ensure that the bridges are in good condition. Various sensors are used for this so that if the sensor outputs become abnormal, somebody can fix it and the accidents can be avoided. These sensors tell us if a bridge gets weak at some point so that they can be fixed before the bridge can break, isn't it? So imagine how we can do this. How do we ensure the good condition of rails? Is this necessary? Maintaining the condition of rails? Of course it is, because there are various lateral and vertical forces acting on a rail. If we are able to keep a proper track of all these forces, we can very easily tell if a certain track needs repairing. And can we measure how many big vehicles or small cars pass a certain length of road? See, imagine that a certain group of people want to monitor traffic in some area. They might be interested in knowing how many heavy vehicles like trucks, buses, and how many lightweight vehicles like cars traveled on a particular road during a specific time period. So we need some means by which we can count these vehicles. How to achieve this? Now all these tasks, they can be done by a variety of sensors, but all these tasks can be also achieved with the help of a sensor called as strain gauge. So this is our today's point of discussion. We are going to see what is a strain gauge. Yeah, so these are some pictures. For example, measuring stress level of aeroplane wing. So this is a picture of what was done in olden days. People actually used to stand on the wings to measure how much stress they can bear. Whereas this is a plain wing and a lot of sensors nowadays like strain gauges are mounted on this. The strain is applied and we get the readings. Yeah, so this is like maintaining bridges. As I told you, strain gauges, so these are strain gauges which are mounted below the bridges. Now here if you want to measure lateral stress, they are also connected across the columns which are raised while constructing the bridges. So output of these strain gauges can be monitored. So this is something maybe people might be doing in olden days. Measuring rail forces. So these are the rails. And as I told you, there are vertical as well as lateral forces acting on rail. And various strain gauges are used in various positions that we will see later to measure such kind of forces, and these forces, the outputs of these strain gauges are continuously monitored so as to have a proper indication. Now let's have a look at working principle of strain gauge. If a metal conductor is stretched or compressed, its resistance changes. I repeat, if a metal conductor is stretched or compressed, its resistance changes. Why? There are three reasons. Because maybe its length changes, its diameter changes, its resistivity also changes. So let's imagine this metal conductor. So this original diameter was D0 and length was capital L. Now I am trying to stretch this from both the sides so that the diameter now has changed by a very small amount delta D and length has increased by a very small amount delta L. But what actually what happens so that the resistance of this changes? This can be very easily stated by this formula which is very well known to us. R is equal to rho L by A, whereas rho is called as the resistivity D is the diameter, which ultimately affects this cross-sectional area here, and length. So as length changes, diameter changes and resistivity changes, the resistance of this conductor also changes. And if we can measure the resistance by some means, we can actually measure how much amount of force is applied to this conductor so that it got stretched. Or sometimes we also apply force so that it gets compressed. This phenomena wherein the resistance of material changes because of its resistivity changes is called as piezoresistive effect. Continuing with the working principle, we know that this was the original length. We have applied a force and now the length is L plus delta L, and we are also aware of this formula, R is equal to rho L by A. Now if we are interested in finding by how much amount the resistance has been changed, we need to find the derivative of this rho L by A. Simplifying further, we get this, and ultimately delta R by R is equal to d rho by rho plus 1 plus 2 mu into strain. This expresses the basic proportionality between resistance and strain in the gauge element material. So yeah, we can see how much strain we have applied, that much change in resistance per original resistance we get. Now this is something very important, the gauge factor. The measure of sensitivity of the material or its resistance change per unit applied strain is defined as the gauge factor. So in terms of a formula, it is given as gauge factor is equal to change in resistance per original resistance. So before applying any strain, if the resistance of conductor was capital R, let us assume that now there is a small change in resistance called as dr. So this is the change in resistance per unit original resistance, and this is the applied strain. From previous equations, gauge factor can also be determined by this. And very important factor is gauge factor gives the sensitivity of strain gauge. We all know that. What is sensitivity? It is output divided by input. So output is change in resistance per original resistance, whereas input is the applied strain. So by gauge factor we mean sensitivity of strain gauge. Yeah, so this is the final formula for strain gauge, whereas this factor is because of resistance change due to change of length. This is because of resistance change due to change in area, and this is because resistance change due to piezoresistive effect. The strain is usually expressed in terms of microstrain. So we have studied in last lecture that strain is a unitless quantity because it is change in length divided by original length. So it's unitless quantity, but it is very small. Therefore, it is usually expressed in terms of microstrain. So whatever is given as microstrain, don't forget to multiply it by 10 to the minus 6. If the change in value of resistivity of a material when strained is neglected, the gauge factor is given by 1 plus 2 mu. So if it is stated in the problem that please neglect the piezoresistive effect, you can straight away go for this formula here. The Poisson's ratio value of mu for all metals is between 0 and 0.5. This gives the gauge factor of approximately 2. If it is not given in formula, you can assume the Poisson's ratio as 0.3, which gives you a gauge factor of 1.6. So this is value, or these are the some materials which are used for constructing strain gauges. Have a look at them. And so how to measure this change in resistance, because it is very small. So most common method here is the Wheatstone bridge that we all have studied. So we will look into various circuits of strain gauges using Wheatstone bridge in the upcoming lecture. Thank you so much.